First came that dense, eerie fog, clinging close to the ground and making it hard to see. Then the wind started picking up, hot and howling, scattering debris everywhere. Soon enough, fires sparked out of nowhere, fed by the dry air and spreading faster than anyone could contain. All the while, strange booms echoed from beneath the earth.
Oh my god, did you guys hear that?
Signaling that something big was still churning below.
Dense, swirling fog settles over the landscape, a foreboding signal of what's brewing deep below the surface. As magma forces its way through cracks and conduits beneath the volcano, immense pressure builds. This pressure can lead to sudden, ear-splitting booms and explosions. Within the volcano's hidden chambers, bubbles of volcanic gas violently burst, sending tremors through the ground. Superheated hydrothermal systems, like scalding kettles beneath our feet, can resonate with a roar. And all the while, tiny earthquakes, known as harmonic tremors, create an ominous hum that grows in intensity and then abruptly silences, a telltale sign of impending eruption. As the fog thickens, scientists observe more clues. Columns of steam, or fumaroles, rise from newly heated ground, and the earth itself begins to swell, straining at the seams. Instruments detect shifts in heat flow and changes in volcanic gas composition, especially sulfur dioxide. Each new wisp of smoke and each small quake brings us one step closer to a cataclysmic event. Under the right conditions, the sheer force of escaping gases and rising magma can spark firestorms and violent windstorms, adding yet another layer of chaos to an already apocalyptic scene. When you hear the thunderous blasts echoing across the valleys, and when the ground shudders beneath your feet, you'll know the volcano is on the verge of unleashing its power, taking the fog and everything else in its path into a fiery tempest that will alter the landscape forever.
Our planet is showing signs of change. Strange events are happening around the globe. Dense fog has blanketed cities, obscuring familiar landscapes. Volcanoes, once slumbering giants, have roared to life, spewing ash and fire into the sky. Wildfires rage across continents, leaving behind a trail of destruction. These occurrences, while seemingly disparate, may be linked by a common thread. Scientists are investigating whether these events are connected to a larger phenomenon, rising magma beneath the Earth's crust. From the fog-choked streets of London to the fiery slopes of Mount Etna, the Earth seems to be sending us a message. Is this a series of unrelated incidents, or is something more profound at play? The timing and intensity of these events have captured the attention of scientists worldwide. Could these be signs of a planet in flux, responding to forces deep within its core? The quest for answers leads us on a journey into the heart of our planet, where molten rock flows and tectonic plates collide. Could the Earth's fiery underbelly hold the key to understanding these recent events? Some scientists propose a bold hypothesis. Rising magma is driving a cascade of environmental and geophysical changes. This idea offers a compelling explanation for the seemingly unconnected events we've witnessed. The rising magma hypothesis suggests that changes in the Earth's mantle are pushing molten rock closer to the surface. Magma, the molten rock found beneath the Earth's surface, is a powerful force. As it rises, it can heat underground water sources, creating steam vents that release gases into the atmosphere. These gases, combined with water vapor, can condense into thick fog, blanketing cities and disrupting transportation. The heat from rising magma can also dry out vegetation, creating ideal conditions for wildfires. Furthermore, the pressure exerted by magma can trigger earthquakes and volcanic eruptions. The rising magma hypothesis is supported by a growing body of evidence. Scientists have observed increased volcanic activity, rising ground temperatures, and changes in the Earth's magnetic field, all of which could be explained by magma movement. If this hypothesis proves true, it could have significant implications for our understanding of the Earth's systems and our ability to predict future events. It would mean that the planet is more dynamic and interconnected than we previously thought. While the rising magma hypothesis is still speculative, it highlights the need for continued research and monitoring. Understanding the forces at play beneath the Earth's surface is crucial for predicting and mitigating the impacts of natural disasters. The quest to understand our planet's inner workings is a continuous journey, and the rising magma hypothesis is just one piece of the puzzle. Deep beneath the Earth's surface, hidden from our view, flows a river of fire. This molten rock, known as magma, drives the processes that shape continents and fuel volcanic eruptions. Magma is a complex mixture of molten rock, gases, and crystals. It evolves under immense pressure and heat. The Earth's interior is layered, with the crust forming a thin skin over the mantle. The upper mantle, where magma originates, behaves like a viscous fluid. Temperatures can reach thousands of degrees Celsius, creating magma. The composition of magma varies, affecting its viscosity and eruption style. Understanding magma helps predict volcanic behavior and the forces shaping our planet. The Earth's mantle is a dynamic system driven by heat from the planet's core. This heat creates convection currents, circulating like boiling water in a pot. These currents drive tectonic plates and the upward migration of magma. Heat from the core warms the mantle, causing it to rise. As it rises, it cools and sinks, creating convection cells. These cells move tectonic plates, causing earthquakes and volcanic activity. Magma rises towards the surface, accumulating in magma chambers. This can trigger volcanic eruptions and create new crust at mid-ocean ridges. Section 3. A cascade of consequences, magma's impact. Magma's ascent triggers a cascade of consequences impacting the atmosphere and biosphere. It releases heat, gases and fluids, altering Earth's systems. Rising magma can lead to volcanic eruptions. Pressure buildup in magma chambers can cause eruptions. Eruptions range from gentle flows to explosive blasts, affecting air travel and climate. Magma can create geothermal features and release greenhouse gases. It can also melt permafrost, releasing methane. The interplay between magma and Earth's surface has far-reaching consequences. Understanding magma's impact helps us prepare for volcanic hazards and climate implications. Section 1. The Fog Blanket, an atmospheric enigma. A pall of fog has descended upon the planet, shrouding cities and landscapes in an eerie mist. This persistent haze lingers for days, disrupting transportation and daily life. Reports of unusual fog have been pouring in, with meteorologists struggling to explain its persistence. Theories range from unusual weather patterns to industrial pollution. Could there be a connection between this global fog and volcanic activity? The fog's composition raises questions. Analysis reveals higher levels of sulfur dioxide, hinting at a volcanic link. The scale of this fog event points to a widespread source, possibly smaller vents or fissures. The fog poses challenges to transportation, air quality, and mental well-being. Reduced visibility has led to flight cancellations, traffic snarls, and maritime accidents. Prolonged exposure to dense fog can exacerbate respiratory problems and cast a gloomy atmosphere. The fog serves as a reminder of Earth's interconnected systems, where deep changes manifest as surface anomalies. Section 2: Volcanic whispers, gases, and steam vents. Scientists study volcanic regions linking rising magma to gas release. Steam vents release superheated steam and gases from underground. These vents act as safety valves in volcanically active areas. Magma heats rocks and groundwater, releasing gases like sulfur dioxide. Gases rise through fissures, escaping into the atmosphere. Normally, vents release small, barely noticeable amounts of gases. Increased magma movement could activate existing vents and create new ones. Gases condense into fog or haze upon reaching the cooler atmosphere. Sulfur dioxide aids fog formation by acting as condensation nuclei. Volcanic gases in fog hint at a link between rising magma and atmospheric changes. Section 3: Data speaks, correlations and anomalies. Rising magma hypothesis gains credence from data showing correlations and anomalies in meteorological and seismic records. Scientists notice unusual spikes in humidity and barometric pressure coinciding with increased seismic activity. Meteorological stations report significantly higher humidity levels, often exceeding 90%. High humidity levels and volcanic gases suggest a source of moisture beyond normal atmospheric conditions. Barometric pressure readings show unusual fluctuations, indicating changes linked to underground gas release. Pressure anomalies coincide with swarms of small earthquakes near volcanic vents. Seismic data reveals an uptick in activity in volcanic regions worldwide. Scientists detect an increase in earthquakes in volcanic areas, including new or more active steam vents. These seismic signals provide insights into magma movement beneath the Earth's surface. Section 1: The Earth catches fire, wildfires rage. Across the globe, wildfires have engulfed forests from the Amazon to Australia, burning with unprecedented intensity. These fires defy traditional explanations, leaving devastation in their wake. Firefighting resources are stretched thin, raising concerns about long-term impacts on ecosystems and climate. The familiar orange glow is a haunting reminder of our planet's vulnerability. Smoke chokes the skies, impacting air quality and creating hazardous conditions. Vast areas are consumed, releasing greenhouse gases and exacerbating climate change. The human toll is immeasurable, with homes destroyed and lives lost. Communities are displaced, forced to flee and leave behind memories. The psychological scars will linger long after the flames are gone. Scientists and policymakers question if these fires are a symptom of climate change or something more profound. The rising magma hypothesis offers a compelling explanation for the ferocity of these wildfires. Section 2: Magma's blazing touch, igniting the inferno. Wildfires are surging. Could rising magma be the cause? Some researchers believe magma's heat ignites blazes. Methane released by magma can spark wildfires. Pyroclastic flows incinerate everything in their path. The rising magma hypothesis connects Earth's systems. Satellites provide a comprehensive view of global wildfires, tracking their spread and impact. Instruments like NASA's MODIS and ESA's Sentinel are crucial for monitoring fire activity. They capture heat signatures through smoke, creating detailed fire maps. These maps reveal the alarming extent and intensity of wildfires. Satellite data shows increased fire activity and longer seasons. Smoke plumes travel thousands of miles, affecting air quality. Satellite data helps study wildfires' long-term impacts on ecosystems. Researchers assess carbon release and climate change contributions. Satellite insights are crucial for understanding wildfires and climate change. The Earth, often perceived as solid and permanent, is in a constant state of flux, its fiery underbelly a realm of immense power. The movement of magma beneath the Earth's crust leaves behind telltale signs, whispers from the depths hinting at the forces at play. Scientists use sophisticated instruments to decipher these whispers and understand the potential consequences for our planet. One dramatic sign of magma's ascent is the awakening of dormant volcanoes, rumbling back to life after centuries of slumber. These volcanic reawakenings are often accompanied by increased seismic activity, ground deformation and gas release, indicating rising magma. Ground fissures, cracks in the Earth's surface, can stretch for miles, releasing plumes of steam and gases. These fissures, often associated with volcanic areas, can signal magma intruding into shallow depths, fracturing the overlying rock. The appearance of new fissures or the widening of existing ones can indicate increased underground pressure, potentially signaling an impending eruption. Even in non-volcanic areas, subtle signs of magma's ascent can be detected. Geologists use sensitive instruments to measure ground uplift, indicating magma accumulating at depth. This uplift, measured in millimeters or centimeters per year, can be a crucial indicator of magma's movement and its potential impact on the surface. Scientists seek not just signs of magma's presence, but also its fingerprints, the unique patterns that distinguish its influence from other geological processes. From heat anomalies detected by satellites to seismic swarms recorded by seismometers, these fingerprints provide crucial clues for understanding magma's upward migration. One telling fingerprint is the detection of heat anomalies, areas where the Earth's surface temperature is significantly higher than expected. Satellites equipped with thermal imaging sensors detect these anomalies, often coinciding with areas of known volcanic activity or increased seismic activity. These heat anomalies can indicate shallow magma bodies releasing heat into surrounding rocks. Another fingerprint is the occurrence of seismic swarms, clusters of small earthquakes triggered by magma moving through cracks in the Earth's crust. The frequency, intensity, and location of these swarms provide valuable information about magma's location and behavior. Perhaps the most intriguing fingerprint is the detection of shifting magnetic field lines, subtle changes caused by the movement of conductive materials like magma. The Earth's magnetic field, generated by molten iron in the core, fluctuates over time and can be influenced by magma movement in the crust and upper mantle. These fingerprints help scientists understand the scale and potential consequences of magma's upward migration. Section 3. A chorus of experts deciphering the Earth's messages. The investigation of the rising magma hypothesis has brought together experts from various scientific disciplines, each contributing their unique perspectives. Volcanologists analyze eruption patterns, gas emissions, and ground deformation data to understand magma behavior. Seismologists use seismometers to monitor ground vibrations, tracking magma movement through the Earth's crust. Geochemists analyze volcanic gases and rocks, seeking clues about magma's origin and evolution. Geophysicists use techniques like gravity surveys and electromagnetic imaging to create images of the Earth's subsurface. This collaborative effort is crucial for understanding the complex interplay of factors contributing to magma movement. The rising magma hypothesis highlights the interconnectedness of Earth systems and the need for a holistic approach. The scientific community recognizes the potential implications of the hypothesis for volcanic hazards, earthquake prediction, and climate change. The quest to understand Earth's fiery underbelly requires collaboration, innovation, and respect for the planet's power and complexity. The Earth's interior is a realm of immense heat and pressure where solid rock can flow like a viscous fluid over geological timescales. Driving this dynamic system is a combination of forces, both internal and external, that create the conditions for magma to rise and shape landscapes. Understanding these forces is crucial for unraveling the mysteries of the rising magma hypothesis. One primary driver is the Earth's internal heat engine, powered by residual heat from its formation and radioactive decay. This heat sets the mantle in motion, creating convection currents that carry heat and material towards the surface. These currents interact with the lithosphere, causing it to thin, stretch, or break apart, creating zones of weakness for magma to rise. The rising magma, less dense than surrounding rock, exerts pressure on overlying rocks, creating pathways for ascent. The weight of the overlying lithosphere also influences magma movement. In regions with thicker lithosphere, the pressure can suppress magma ascent, keeping it trapped at depth. In regions with thinner lithosphere, reduced pressure allows magma to rise more easily, leading to volcanic activity. These forces work in concert to create the conditions necessary for magma to interact with the surface. The movement of magma is influenced by both internal and external factors, creating a complex interplay between Earth systems. Understanding this interplay is crucial for predicting magma behavior and its potential consequences. One external factor is the melting of glaciers and ice sheets. As glaciers melt, they remove weight from the Earth's surface, causing the lithosphere to rebound upward, a process known as isostatic rebound. This rebound reduces pressure on the mantle, allowing magma to rise more easily, potentially triggering volcanic eruptions. Another external factor is the gravitational pull of celestial bodies like the Moon and the Sun. These tidal forces, though weak compared to Earth's internal forces, can influence magma movement. The interplay between these forces creates a dynamic system where subtle changes can have cascading effects. For example, glacier melting, driven by climate change, can trigger isostatic rebound, influencing magma movement and potentially triggering eruptions. The rising magma hypothesis highlights the interconnectedness of Earth's systems and the need for a holistic approach. By studying the interplay of forces driving magma movement, we gain a deeper appreciation for the delicate balance of our planet. Understanding this balance is crucial for predicting and mitigating the potential impacts of increased magma activity. Our planet is a system in flux. The rising magma hypothesis highlights the immense power beneath our feet. It underscores the interconnectedness of Earth systems and the potential impacts on climate and hazards. Increased research and monitoring are crucial to understanding and mitigating these impacts. Respecting nature's power and embracing responsible stewardship is essential. In the face of uncertainty, knowledge is our most powerful tool. Navigating the rising magma hypothesis requires vigilance, collaboration, and evidence-based decision-making. Scientists, policymakers, and the public must work together to address these challenges. Sharing findings and uncertainties fosters informed skepticism and continuous learning. International collaboration is essential for a global perspective. Policymakers must make informed decisions on resources and preparedness. Public engagement is crucial for understanding and responding to risks. The rising magma hypothesis sparks a global conversation on nature's power. This conversation must continue, guided by scientific evidence and collaboration. Embracing the unknown and working together creates a sustainable future.